Hi, everyone. Welcome to our last but not least pre-conference keynote. So today we have the honor to have Elias Bareinboim to teach us about causality. And before we get started, I wanted to say a few words. So first of all, I'd like to thank our very generous sponsors, the Alfred P. Sloan Foundation, the Center for Research in Economics and Strategy at Washington University, and the Desatel Center for Integrative Thinking at the University of Toronto. So thank you very much for providing the resources to make this very interesting interdisciplinary workshop happen. So the idea of this workshop is to stimulate interdisciplinary conversations about interactive causal learning. The ability of using causal models to guide behavior is now being recognized as an essential feature of intelligence in many scientific circles. And recently, there has been a burst of interdisciplinary research bringing together scholars from causality and machine learning. So the goal of this workshop is to bring two additional disciplines to this conversation: game theory, economics, and philosophy. And now, because it's very hard for people from different disciplines to understand each other, the point of this pre-conference keynotes is to bring world-class scholars to provide at least a little bit of grounding, as well as to give an idea of the recent developments and outstanding issues in each of these areas. So we already had 3 pre-conference keynotes in machine learning, game theory, and philosophy. So you can check them out in our website. And today we're going to have our keynote on causal inference with Elias. And talking about language barriers across disciplines, I personally think that the recent mathematization of causality may be an important piece to bring scholars together. So we have seen the emergence of a unified mathematical framework that allows us to formally address several disparate cross-disciplinary issues. For example, we can characterize fundamental limitations of deep learning, formalize philosophical problems of fairness and actual causation, or address problems of the generalization of cause effects across domains, all within a common mathematical framework. So with that said, I would like to turn over to our speaker today, Elias Bareinboim. So he's perfect for this job. So Elias is an associate professor in computer science and the director of the Causal AI Lab at Columbia University. He is the recipient of many awards, and he's currently at the forefront of causal inference research, focusing both on causal and counterfactual inference in the sciences, as well as in artificial intelligence and machine learning. So he has pioneered work in many areas, such as the problem of data fusion and the generalization of causal claims, as well as the application of causality and the intersection of causal inference in reinforcement learning and fairness analysis. So Elias, now the floor is yours. So you're already host, you have all the power. You can take it from here. And in terms of time, we have until 10:30 a.m. So it's up to you whether you want to take questions at the end or if you want to take questions during, and then we just go until 10:30 a.m. And you take the questions during the talk.
Thank you, Carlos. Thank you. I will take questions. I can take throughout, but if I feel that is not the most important for the understanding of at least this piece, I will just say, let me postpone and take it at the end. But feel free to interrupt me, and then I will see. I will decide if I want to address on time or not. But you can try. But anyhow, before that, good afternoon, everyone. Thank you, Carlos. Thank you, Michael, Danny, and everyone for the invitation. I'm happy to be here today. It's 12:08 New York time. I'm Elias. I will be talking about causal data science, a general framework for causal inference and fusion. By the way, Carlos, if you can interrupt me and tell if there are questions. Otherwise, I will not be looking into the chat.
Okay, I'll be monitoring. So for the attendees, you need to raise your hand, or you can ask questions in the chat. And for the panelists, I would also ask you to raise your hand, but you can also just unmute yourselves.
Right, sounds good. Because otherwise I'm following the chat. I will delegate that to you.
Okay.
Thank you. Anyhow, I'm Elias. I'm professor at Columbia University. I'm usually on Twitter. Follow me there. Usually there are interesting discussions, and if you want to exchange some ideas and talk with me. As I said, today we'll be talking about causal data science, a general framework for inference and fusion. And in some way from my through computational lenses, I would say there's a kind of diverse background here in the room. I will give, I think, the computational perspective on the problem. The idea is to try to share a little bit of the research program that I have been developing for some time now, maybe 12 years or so. I start kind of more abstractly and then trying to give more concrete examples. Importantly, the emphasis will be more introducing the ideas and maybe the formalization or some part of the formalization, as Carlos said. I will not enter in the details of the solutions. Usually you take the whole course discussing the solutions for the problems that we are here. By now, excited. Without further ado, I'd like to start with the aspirations and challenges of data science, and starting with the idea or the note by Professor Hal Varian, there's also chief economist at Google and professor in Berkeley, saying this is about the ability to take data, to be able to understand it, to extract value from it, to visualize it, to communicate it. That's going to be hugely important in the next decades. Then we have a professor, university professor in Harvard, political science and statistics, called Gary King, saying the big data is not about the data. And then we have Professor Yuda Pro in computer science and statistics at UCLA, saying that data science is only as much as of science as it facilitates the interpretation of data. A two-body problem connecting data to reality, I think is kind of representative in the field in some way, because someone is saying, oh, it's all about the data. Someone is saying not really about the data in some way, and then Yuda is saying, oh, there's something about the data plus something else, as the data connecting to outside reality. And I hope that, and I think it's kind of, anyhow, it's important to have in mind these different perspectives in some way, and I will try to share how to instantiate that in the specific problems that we have in the field. But I think part of this tension also relates to this, what professor of medicine in Stanford, John Ioannidis, says that why most published research findings are false, and I think it's quite acute that they are usually not reproducible, not robust, and we have all kinds of problems when you kind of zoom in some of these papers. And we spend kind of billions of dollars trying to produce these research results. There is a lot of good intention and goodwill. Some of the best and the brightest of our generation are trying to solve some of the puzzles that we have in science, and broadly more in AI and ML, that intersection with society and other kinds of problems. And still, the results are very brittle and they're very fragile in some way. Then the question, why this is happening? And then I think by the way, my hypothesis is related to the lack of causal inference capability of having a proper causal language. And I will try to elaborate or defend this point throughout the talk. Then the goal of the talk here will be in the agenda that I'm part of is to develop a causal inference engine. This is the materialization of a language, algorithms, guarantees, tools for performing data fusion, and I'll focus here about population level interventions by cohesively combining multiple heterogeneous data sets. This kind of view is going on for many years, but there's a nice summary in this paper that I wrote with Yuda in the proceeding of the National Academy called Causal Inference, the Data Fusion Problem. Oops, what happened here? Oh, I click it's linkable. They opened my browser here. And this comes a companion paper that is more recent that I also recommend is this on Peirce's hierarchy and the foundations of causal inference, that kind of grounds about a little bit more the discussion about the assumptions related to these types of inferences that we're discussing here today. Another recommendation of reference, I think most of you may be familiar, but if not, recommend also the book by Uda Pro and Dana McKenzie that's called The Book of Why. It's kind of giving a bird's eye view, a kind of summary of what's happening in the field for a long time. Hopefully we'll try to mathematize some of these results here. And this is our goal. Is this thing called data. Everyone is very excited about the huge amount of data that we have. I am excited as well. The challenge that you mentioned and start the paper, the PNAS paper, is like all data is not created equal. That's the original observation. Sounds general, but what does it mean? There's a lot of data out there, but the data is almost invariably collected under different experimental conditions. The underlying populations are different. The sampling procedure is not randomized. The treatment assignment is not randomized. And many variables are not measured, or they are not measured consistently across the different data sets. In other words, the collected data or the data collection is messy and rarely perfectly matches the inferential target. Then the premise of the existence, I would say, of the field, or why we're spending our time with that, is like the data collection is messy. If it was perfect, the joke in machine learning is like you can put just a bunch of monkeys typing and eventually things will converge. You're just kind of summing, and by the law of large numbers or the CLT, things will be okay. The challenge here and why we exist and what do you need is exactly because there is a mismatch between the types of data that we are collecting and the types of claims that we are trying to make about the underlying reality from where this data come from. Then that's the initial motivation. Jeremy, do you want to ask a question?
No, thanks. Sorry, it was an accident.
Oh, okay. Then this is our very motivation. Now, it seems kind of tough. The positive here, and the point that I want to convey is like all these dimensions that I mentioned, that there is the mismatch, are now formalized. Then you have a formal language to exhibit this, to talk about this type of mismatches. And also there are conditions and algorithms to decide what is entailed or inferable from a certain data collection. I'll try to elaborate what this means. One example about this word heterogeneous is super overloaded. I'll talk in the heterogeneous in some sense here. First, assume that we have this target, and try to give the example. Let's say that we have a target quantity Q that is equal to the P star of Y given to X. I think most are here familiar from the other keynotes. This, of course, is very different than the P star of Y given X. This would be a classifier, a typical machine learning type of object. This is a causal inference object. In another notation, we could also write P of Y sub X, but of course, different than saying Y given X. Now I have these different data sets, data set 1, data set 2, data set N. And now I would like to go over the dimension. The first dimension that I mentioned, we are collecting data from different populations. Maybe one data is from New York, one population is New York, the other population is Boston, the other is Texas. For example, this is one dimension. That the New York people is different than Boston people, of course. Second dimension, what is the kind of, is it observation or experimental? Now, the data in Boston was observation. It was passively connected through some sampling, random sampling, and while D2, or the first data set, it's experimental, there is random sampling, but there is also the random assignment of the treatment, and importantly, usually also is not only observation experimental, but what was controlled, or what was randomized. In this particular data set, in New York, it was randomized as variable Z1. Again, I was saying there is a mismatch. Note that our goal here was the X. We're trying to make the claim about Y do X, but we have data that was randomized, some kind of do Z1 data set. And here you have a do Z2 data set. And this is the dimension 2. The other dimension is the sampling. Perhaps there is the selective pressure here that people from older age is more overrepresented in this particular data set. Maybe you are calling the landlines and people, I don't know, over less than 40, but maybe, sorry, less than 30, less than 40 don't even have landlines nowadays. Then, of course, we are overrepresenting and some, they skew towards a certain population. And also the data, we don't, not all variables are measured consistently across data sets. We have different columns in each data set. This is just an instantiation of that. And those are the dimensions that we have, and I would like to talk about. It turns out that there are different tasks related to these different dimensions. I would like to discuss that. I say causal data set, task and dimensions. Some common inferences in scientific circles, AI and machine learning, involving some standard assumptions. I will list some tasks and try to understand where we are in the world. By the way, everything here is a personal view. You may have your own opinion. This is my reading of history, I should say. The first one starts from statistics, an important and very challenging inferential type of problem or leap that we have, that we are trying to move from something that is specific, that is samples from one distribution, from one population, to the distribution itself. Distribution is just abstraction. You have samples that is something concrete or data, and you are trying to make the claim about this distribution. Many people work on that for hundreds of years in reality, depends on how you cut history. I'm giving credit here for some of the people that I think help in a substantive way formalizing this arrow here. Nowadays, it's so common, it's a kind of cracked problem that we fundamentally understand how to go from sample to distribution. Despite the practical challenges, the theory is very solid and robust. And what I mean by that is there's something like the law of large numbers, Bernoulli is a representative here, or central limit theorem, or the delta method, and so all these kind of results that allows us to go from sample and make a claim about this underlying object that is the distribution itself. Now it took a few years, a few decades, until we have another problem that I like to call experimental statistics. That now there's a new animal here in the room, that we are no longer passively collecting the data, but someone has idea, and I attribute huge credit for Fisher for the idea of how to systematically control the population, or how to randomize the treatment. The idea of randomize the treatment assignment, again, that taken for granted nowadays. It was one of the biggest discoveries from the previous century. And now, once we can access the dual distribution, now we have a similar problem that we are moving from the samples of the distribution to the distribution itself. We're just moving from OBS to the dual. It was a big deal. I'm giving credit also for Fisher, Cox, and Cochrane, and some others, I should say, that help us to do that. And it is a discipline. Now every university, every stats department has an experimental design or experimental statistic type of course. Now there's a different beast here. This is the one that most of us are interested, I believe, that is called the causal inference. I would like to articulate this is causal inference from observational studies. Very important. It was studied for a long time. Different beast, different animal, because we are no longer from samples to distribution, but now we have the distribution OBS. This is the arrow here. How can you move from a different regime or different distribution OBS to as if you did the experiment in the population? Well, another way to see is like you are moving from this distribution here to this distribution here. It's no longer kind of horizontal, but it's a vertical type of move. This is my reading, I would say, causal inference from 1974 until 2011, it's a huge amount of time, was mainly concerned with something called confounding bias. Confounding bias is nothing more than the difference between these two distributions, and has been essentially solved theoretically. This is the way that I read history by Don Rubin, Robbins, David, and Pearl. In the sense that despite the technical challenges, I do feel that we understand very much under which conditions can you move from OBS to the DO. And this is a huge achievement. Now, normal question here, I didn't get this one. I think if I'm reading the whole place here, I don't know where the questions are coming from. But usually I get, Elias, are you saying that we are done? Because, wow, that's amazing. If it's true what we're saying, wow, that's good. Some people could say slightly more adversarials, but not necessarily saying, oh, but those are known things, Elias. When does the causal data, is this causal data science, or where causal data science comes into play? And I would like to elaborate. And I would like to apply a computer science trick here, parametrize, or a math trick. Parameterize these problems that we discuss in terms of the dimensions that I listed before. D1 was the population, D2 was observation experimental, D3 was sampling, D4 was what is measured. Again, from the PNAS paper that we have there. Now I will move here. Done. I just applied the parameterization, and I'm highlighting now what is changing and what is not changing in the particular task. Just to pick an example that may make more sense and we like. For example, this guy here, I'm saying that we're talking about the same population D1. you have the same kind of sampling. There is no issue of sampling here. This is the sampling D3. We have the same variables that you care about, D4, D4, and we are moving from OBS to the DOX. And that's nice. Question, just rephrasing here what was asked before, do these dimensions exhaust all the possible data collection modes? The answer is no. And I would like to elaborate. Then I'm just copying exactly this line to the top of the slide, giving the credit for who I believe the credit is due. Partially, there are other people involved, but I think those are some of the proponents or of the solutions or articulation even of the problem. Now I'd like to go to another problem that I like to call experimental inference or generalized instrumental variable. Now, instead of moving from OBS to the DOX, we would like to move from the DOZ to the DOX that we have before. I say the DOZ1, remember, in the previous 2 or 3 slides ago, but let's say DOZ to the DOX. It's a different beast. I'm not the first to talk about this problem. There is the family there, Philip and Cyril Wright, in 1928 articulated the first version of this problem in some kind of parametric setting, but anyhow, they are concerned about this type of inference in the constant of IV. It could be any other. IV is just one example. Instrumental variable is just one example of this type of inference. Now, another problem that I would like to articulate related to dimension 3. This is dimension 2. Related to dimension 3, selection bias. Maybe let's fix the 1, the 2, and the 4. And now we have this selective pressure on age that I mentioned about the landlines before. Then the data on the left is skewed towards older people, and you would like to make a statement, I'm putting this way to say, is about the overall population. Whatever set of covariance and distribution we have the population, or composition, I should say, of the units in the population, we like to match that in some sense. Not the matching, but we like to have that, we like to be representative in some way. Again, it's not a new problem. This started the professor in the University of Chicago called James Heckman in 1976, showed the first example about it is possible to recover from sampling selection bias. If you have the data in the left, there is something that we can do to get the data in the right, to make the data as if you have the data in the right about the population without the bias. And his context was an econ type of context. And then there's a boom of works trying to generalize his results. Remember, this is our dimension number 3 here. Again, my reading of history. Maybe you can give credit to others and see and slice it differently. Now, the fourth one that I like a lot is called transportability, or also known as external validity in the sciences. This is related to dimension 1. Maybe in the extreme case, we have data, it happens all the time, we have data about some of our cousins. The bonobos is a type of monkey, and maybe you like to make a statement about Homo sapiens, about us. And again, it's about this arrow here, under what conditions can we do that? Again, I'm not the first to talk about that. This is starting my PhD, you shared me this book. There's the quasi-experimental design by Shadish, Cooker, and Campbell. This may be 2009 or 2010. That they are kind of start trying to get some kind of, I would say, it's fragments about how to move from the left to the right. My observation here, special cases of the dimensions have been addressed in the literature, mostly in isolation and under very special or not so special, but usually special parametric conditions for sure. In practice, they appear all together in what I like to call, and hopefully you call as well in the future, the causal data science. In other words, you have a data collection that is in this, is a tuple in these 4 dimensions in the left, and it could be many data sets, and we have some kind of target population with the star dimensions, the 1, the 2, the 4 star. And the questions like under what conditions, this arrow here, can you do that in general? Which kind of assumptions you need to move from the left to the right. Now, for the sake of practicality, I said that I start kind of more general. I like to try to be a little bit more concrete and discuss one particular problem. We spend the whole semester, in reality 2, the whole year in 2 classes discussing these tasks. I'll just pick one and try to give the flavor about how to think about these problems and what could be, what I would consider this is, I make this is solved on the CS side. What does being solved could mean even in practice. I see that some people, depending on the field, get uneasy about that. I'll try to be specific and give you my view. Another more realistic here in the data science, in the left side, maybe you have data that is coming from Los Angeles, from UCLA, from the UDAS hospital there at UCLA, and maybe you'd like to make a statement about what will be happening here in New York City. Now, my goal here, at least at the moment, I would like to talk a little bit more about this task called transportability that is related to the last one that we discussed, is very related to the idea of extrapolation and robustness of causal claims. I usually like to write the problem statement. The problem statement goes as follows, or the first problem statement. Is it possible to compute the effect of X on Y in a target environment, pi star, where no experiments can be conducted, are feasible using experimental findings from a different environment, pi? The answer is sometimes it is possible. The whole goal of the research is trying to understand under what assumptions, or how can you formally characterize when and how these types of inferences are allowed. Another example here that I like, this is very related to this idea of moving from the lab, and I quote here lab, from the lab to the real world. Lab is this small environment. I have these 4 variables here, X, Y, W, and Z. Lab is just a metaphor standing for environment, population, domain, setting, species. Then the lab is the very dear place to us, or to the scientists, the data science, I would say, that is a place that you can do experiments. You can shake the things up, you can turn the system upside down, and you can get knowledge about what's going on in the system, in the lab. By the way, I forgot. I'll say now. I forgot to say. Usually, I have the introduction. I skipped here, but this graph, this causal diagram, and it is called, is nothing more than the parsimonious or non-parametric representation of the collection of mechanisms underlying this system. Now, for example, if you have this variable z, in reality, we are trying to signal that there is this mechanism f sub z that is assigning value to the variable z in the system. There is another mechanism f of x that is listening or taking as the argument, if you want to be formal, the variable z, and assigning the value to the random variable x. You attain the value, for example, small x. W, there is a mechanism f of w that is listening to x. There is the mechanism f of y that is a function of z and w, and so on. Then this is a pictorial way, or parsimonious way, is a serious mathematical object. It's huge theory since Euler and so. But it's a graph, a directed acyclic graph, in this case, that is encoding these underlying mechanisms in the system. And why we're doing that, why we don't talk about the mechanism directly, we don't talk because they are very hard to get in any setting. I think in most settings, maybe all that I care about, or people in AI, machine learning, I would say in data science in general, it's almost impossible to get the mechanism itself. The human is in the loop and things are extremely massive. Then the graph is some type of proxy to this collection of mechanisms. I will elaborate, but just introducing a little bit of notation here. Now, going back to our problem here, we have the lab that is this place that you can do. By the way, Carlos, do you want me to say something else about the graph? I know that you are sensitive to this. You are like the object, but did I miss something?
No, I think no. It's good, Elias.
Okay, sounds good. Appreciate it. Then we have this lab that is this place, a very nice and dear place that you can do the experiments. Usually, even though we like the lab, but there's no fetish about the lab. In reality, we're doing these things in the lab because we would like to make a statement outside the lab, what's going on in the real world. I put even a different scale here, a little bit bigger. Then, first hypothesis I call H1 that the scientists could have is like the lab and outside the lab are essentially the same. It's just a matter of scale, meaning that f of z is equal to the f of z star, that is the mechanism outside the lab. The f of x is equal to the f of x star. The f of w is, if you want to sound better, it's invariant. The f of w invariant across the lab and outside the lab. If that's the case, if everything is assumed to be the same or invariant, things are trivially transportable. Whatever results the scientists obtained in the lab, these will hold automatically outside the lab. And this is one option, the hypothesis H1. You can already see this is very pink. It's very hard to happen because it's usually not the case that lab outside the lab is the same. Reality is not so, is the dream here. It doesn't happen exactly like that. On the other hand, we have the nightmare scenario here that is the following, the opposite side. H2 is saying that the f of z is the mechanism of z is different than the f of z star. The mechanism of x is different than the mechanism f of x star, and so on. And this is called the nightmare scenario because there is no invariance between lab and outside the lab. If you are careful and if you really do some type of science, usually that's not the case. There is something that is shared, maybe not the left-hand side, the left side, but something shared. But still, that's I usually call the nightmare scenario. Very easy case. The yellow arrows is just signaling. I forgot to say, appreciate it. Is just a graphical representation that we are no longer talking about one causal diagram, but now we are talking about the overlapping of two diagrams or two collection of mechanisms. And the yellow arrows are saying that in reality, they may be different. As in any graphical model, the assumptions are not in the arrow, they are in the missing arrow. Then there's no missing yellow here, which means that there is zero claims about what they are invariant. This is the most relaxed in the sense that there is zero claims being made about how they are related. In the left side here, strong, very strong claims because there is a lot of missing yellows. It's not that the yellows are not here, they are here, but someone removed them. They started with the yellow, which means that this f of x, f of z, f of w, they are invariant. But going back here, thanks for the question. Now the continuing here, if everything is not invariant, maybe they may be changing, then the answer from the theory that you like to understand these types of inference is very easy answer. It's the things that there's nothing that is transported. So how can it be? If the assumption everything can be different, can be changing. Then this is again what I like to call the nightmare scenario. In reality, there is a spectrum between these things. There is not like the heavens or the hell, but it's something in between. And my feeling why this is the case is like, whatever, science progresses, we learn things, we do things, then in reality, we are playing in between these two extreme cases of trivial transportability, formally defined in the paper, or the non-transportable in reality, also is formally defined. Now, I would like to pick someone that is in between just to give the flavor, what this could mean. What can experiments in Los Angeles tells us about New York City? Now we have these two populations to be explicit here. Population pi is the one that will conduct the experiment. It's some kind of source population. Population pi star is where we're intending to do the inferences, to perform the inferences that in New York. And then this is our, this graph, by the way, is called selection diagram, at least how we call it in the literature, maybe more than 10 years ago. And this diagram is making the following assumption. Now is a hybrid here in between. There is the yellows pointing to the x and to the z, which means we are non-committal. We are not making a statement about the relationship, which allows to f of z being different than the f of z star, and the f of x being different than the f of x star. But however, or furthermore, there is no y, there is no yellow pointing to the y. The assumption comes here. We are making a strong assumption for whatever reason. After we add z in the system, biology says that population in LA and New York are invariant relative to the mechanism of y. Then the f of y is being assumed to be equal to the f of y star that is here. But you can see my mouse, right? Because I'm moving the mouse sometimes. Is it true? Okay. Then this is our assumptions here in our selection diagram of the overlap of two causal diagrams. Qualitative understanding about the system. Part of the input, and talk about tasks. Another part of the input, we have two other parts. The first one is another piece. This piece is quantitative. We go to LA and you are able to do the experiments and get the P of y given to x, z. And but you cannot do that in New York. But you can get observational data in New York, at least in this setting, which means that we have the observational distribution P star of x, y, z in New York for whatever regulation. It's like maybe you cannot pass, maybe you cannot pass regulation to run experiments here with human subjects in New York. Now, the effect is still well defined. We just can't do it. The one observation here, popping out of this z here, this is a note. the age distribution P star of Z will be different than the P of Z. When you check the data, it's a surface phenomenon, but still in the data, you see the signature, this implication from the F of Z being different, whatever reason, maybe people in LA is younger than New York. Then we are saying that there is a shift here in the age distribution, for example. They are not the same at least. Now, this is our input. Repeating, there's a qualitative piece of the input that is the relationship between the mechanisms encoded in the selection diagram. And we also have two pieces of quantitative input. One is in the source, we have the experimental distribution that we are able to run the experiment in LA. And we are able to collect data from random sampling in New York and get this P star of XYZ. Now, what we want, what is the desirable output? From the analysis, we would like to get to try to know what's the effect in New York itself. The query here that we're chasing is P star of Y given do X. It turns out that for this particular case, I like this picture here because this is the anatomy. This is computational less. The input is very clear. What are the assumptions? The guy on the top here, qualitative. What is the kind of data that we have? These two pieces here. In the left side, LA, in the right side, New York, some different types of data. There's a mismatch between the data and what we want as the output. That is the P star of Y given to X. Then clear, that's the inference that we want to make. Now, it turns out that for this particular problem, the answer turns out to be, we'll get the age distribution or the new age distribution in New York, and you reweight that for each age group by the effect, the age-specific effect of X on Y. Then this is in some way to account for, to observation, to account for the difference in age. The F of Z being different is implying this type of reweighting, if you wish, and in some way, in the second bullet here, interesting enough, it doesn't matter that the X is being different. And in some way, because we're talking about the do, if you try to think about it, what's really happening. Then how X is naturally being assigned, or how people is deciding their own treatment, if they get the drug or don't get the drug. Whether X is drug, taking a treatment or exposure, Y is the outcome and Z is age. And I have forgotten to mention that. But anyhow, but it could be any X, Y, Z, right? Any decision, any outcome, and any set of covariates Z. Now, the name from this formula here, this mapping from this guy is called, I like to call, or we call, you deny the transport formula. Some people like to call the calibration or recalibration. I dislike recalibration extremely, I should say, because it's overloaded. There are so many other fields and so many variations of what calibration could mean, then we're just adding more confusion to the discussion, but whatever, you can pick the name that you want. We presented that I presented that in reality in some seminar at UCLA in the very beginning, and then some demographer came and said, Elias, but why are you doing big fuss out of that? We know that from the England from 250 years ago, he gave the reference. We are kind of, obviously we are not using the do notation, but we are kind of doing the standardization or re-standardization in some sense related to the morbidity rates in the different regions. Then why are you saying that? It's why is this transportability? Why is this new? Why you don't know that for 250 years? I like the question. I didn't realize that someone could say that, but it's very good. It was my fault. In reality, this has been used for a few hundred years now, not necessarily in this syntactical form as the default formula. Then the question that I pose here, or the way that I answered at the time, and I pose here is like, is this a universal law of the data sciences? In the same way that in physics, maybe you have Schrödinger equations, and it's a law. Is this a universal law? Meaning, doesn't matter what are the set of assumptions. It doesn't matter which kind of data we have. This formula, this equality constraint between this functional in white in the right-hand side will always be equal to the guy in the left side. Then I would like to elaborate here. The answer, I think you can already hint, is not true. In other words, they knew and they got it right in some way, but the question is like, under what conditions, again, allow these things to happen. I would like to elaborate on this point, in particular, that the transport formula is sensitive to the causal assumptions that we have about the underlying system. Now I just copy here the same graph that you have before, z, x, and y, the triangle, and I added this dash bidirected. If you don't have latents, at least in this problem, or most of problems, if it's Markovian, the problems are almost always trivial, not necessarily, but almost always. Here, this dash bidirected in reality means that the source of exogenous variations, of the variations outside the system that is affecting z and x, they are not independent. Then in the underlying mechanism of z, there is, for example, this uxz that is unobserved, that also is shared with the mechanism of x, that is the pink guy here. This is a bidirected between x and z. The bidirected between x and y, there is this uxy, this is an unobserved source of variations that is both affecting x and y. And this is what leads to unobserved confounding, and this is why this problem is hard. But anyhow, this is this particular setting here. Now, I just copied the data sets from the previous slides, the experimental data set in LA and the observational data set in New York. And now, the point is like, if you play the same exercise, and I don't show how, I'm just giving you the example, it turns out that you get the same transport formula. In other words, I can get the same data sets here, and I have the same mixture, the same recipe about how to answer the causal effect of x on y in LA, in New York, and this is the mix here of the data that is coming from New York and the part of the data that's coming from LA. In other words, in this particular case, the unobserved confounders are not generating any difference. Now it comes a more interesting case, I would say, I believe. Assume that someone messed up, and now this z here that was age is no longer measured. This is unobserved, and someone is measuring a proxy for age that could be z, that could be the language skill of the units. Now the question is like, and now we have the same data, this z now is just this different variable, do the whole normalization or put them in the same scale. And now the question is, can we use this particular formula that our friend from England, from 250, the demographer, came and asked, can you use the same formula and you still get the effect of x and y in New York? It turns out that the answer is no. In other words, there is no universality of this formula. It turns out that it's just one. The correct way of doing is just getting the marginal effect of x and y in the source here in LA. Two observations here, and I will not elaborate. If you think maybe you'll get, I'm sure that you'll get the same answer. The two observations here, there's a collider. And the S here, I call S by the way, the yellow squares, we call S in this paper, maybe with Hilda, maybe since the beginning, that is just all these exogenous variations that generate the disparity, that could be seen as the disparities between the places. If you condition on z, you are kind of injecting directly these disparities in the variable y. In other words, you are kind of adding the bias in this is the first observation. The second one, the z has no effect or doesn't modulate or doesn't do anything related to with respect to the relationship between x and y. While z here is a confounder and it's kind of changing, the effect of x and y changes with z, here z bear no relationship about the effect of x and y. Then it's oblivious. This is why the formula in some way comes out like that. And the other way, it will add a bias, given that we have this collider here. Idea of some food for thought. Main point here is like this formula, in other words, is wrong. It will be introducing bias if you use this formula, despite of the size of these data sets. Even if they go to infinite, we will never get the guy in the left side. More interestingly, those two cases, the z split treatment happens before x and before x and y. Now, in other words, there's no heuristic here between x and y, because both of them happened before x and y, and still one we use it, the other we cannot use it. Next comment, more interestingly, maybe z could be a biomarker. It could be happening after x. There's just the level. You take the drug, the cholesterol may be changing. You have cholesterol, different distribution of populations in LA and New York. Maybe there is a different Europeans more here, maybe more Asian in LA. Then they have a slightly different distribution of the biomarkers and how that is a distribution of z that you just define this S node here. By the way, I'm just making this up. I don't know in this particular case if this is happening, but just to illustrate here. Then what is the right way of combining the data sets? Assuming the same numbers here, just do the normalization. Same data sets. Is this formula right or the second one, or how do you combine this data? or these data sets, it turns out that it's neither the first formula nor the second. There is a different way of combining these data sets. Regardless of what is the way, again, I'm just trying to introduce the idea, regardless of what is the way, is a different combination, different recipe about how you combine the data.
Elias, we have a question related to the slide 14. So the question is, what does F signify in the F, P, P do, P star?
What's that?
In the previous slide.
Um,
So you had an F. If you go more.
Sorry.
14, yeah.
This one?
No.
The F on the bottom.
Yes.
I'm just, okay, that's a good one. A different F here. Maybe I should put a G here. We're just asking if there exists this G, this mapping, that you take the input distributions. In this case, we have observational distribution in the source. It turns out that we have experimental distribution in the source, and we have observational distribution in the target. Now you are asking if there exists this F such that with this F, this will be equal to the target quantity, that is P star of y given to x.
Okay, thanks.
Hope it makes sense, but yeah, I should put G here. Maybe the F is slightly overloaded. We are running out of letters. But there's a bias towards F, but that's a good one. Thanks. Right now, the point here is like there's different ways of combining the data. Now, again, lesson, lady comes and say, lesson, causal assumptions are required since the data, important. The causal assumptions are required since the data does not impose enough constraints over the causal structure. Then the results are structural sensitive, meaning, this data here that was part of the input do not allow us to distinguish the structures. Point one. Point two, if I get each structure and do the analysis, they are entailing a different combination of the data. Then you cannot be oblivious to the structure. Then is a proof by picture here, but there's no way out. We need in some way to pick this structure or understand this relationship, otherwise we will not cut it. There is no way of solving the problem. Anyhow, I hope it's clear. Food for thought here. We call in the lab FFT, by the way, not the Fourier transform. We call FFT. There are many, some FFT for you. Now I just want to make it crystal more crisp and more CS-like. Crisp algorithm. What we're talking here about now, disconnecting from the example, this is a decision problem. Is the target effect transportable? Now we have three types of input. One is the target query, P star of y given to x. The other is some type of causal model. It could be the causal graph when you are in one domain. It could be the causal diagram in one domain, or selection diagram when you have multiple. And then you have a data collection. If you are, I don't know, Ruby or Perl, you are maybe more in the PV setting. Here we have many distributions in the transportability. Now, the question that we're trying to answer is, based on the current knowledge about the problem that is encoded in these assumptions in the model, and the available data sets that are this number 3 here, is the research question, that is this effect of the new policy or the drug or so, is this effect, the research question, transportable? Again, we are trying to develop this engine. I said that this is the goal that we're pursuing, that you take this triplet as input and will give a solution. A solution in this particular case is a yes or no. If the answer is yes, this means that there is this F, the big F that we talked before. There is a mapping. This is just an example that we discussed before. There is a mapping from the observational data in the target, experimental data in the source, to the target quantity, or the causation in the target. And that's the idea here. But this is what the engine is allowing us to have. This is the problem. I hope that is crisp. What is the problem statement? All the rest will follow from having a clear formulation if you spend enough time. Now, the type of results that we gather, we are interested in, this is a theorem, and I will just give you the general idea. Causal quantity Q is transportable from the source pi to the target pi star, if and only if, this is a strong condition, if there exists a do calculus reduction, the do calculus is some kind of calculus, from this quantity in the domain pi star to an estimate, a function that is a function of the observed distribution, not observational distributions, but the observed distribution. Example here, and I'm gonna go over the derivation, but this is a different graph that is also in the middle of the spectrum. Now the quantity is P star of y given to x, query, and I'll use this graph to do kind of massaging the expression, do some derivation until you get expression thumbs up here, that all of these elements of this expression are observed. This is one piece is coming from the target, that is observation. The other piece is coming from the source, that is experimental. Then this is a positive instance. I would like to, anyhow, this is the theorem. In reality, the hard part here is prove the other side, that in some way, this is also necessary, it's not only sufficient, but I will leave it. I will leave the technicalities. I would just like to show a picture here for the mathematicians in the room that I like a lot, and I use in my class. This is some kind of model theoretical view of what is transportability is trying to do, exactly what we just discussed. Assume that you have this space omega here with all possible causal models in the world. Oh yeah, so a space of all the causal mechanisms. This space is all the mechanisms that are compatible with this diagram G. This space is the space compatible of SEMs that could be generating PV, that is the observational distribution, P star of V, distribution in the target, PV do X, experimental distribution in the source. This is the input that you just put to the engine in the bottom of the previous slide, 2 slides ago. Now what transportability is trying to get is if the area this intersects, if they have the same P star of Y given to X. Each dot here that I'm not drawing is a particular collection of mechanisms. And we are trying to see if this intersection here generates the same distribution that you didn't observe. Let me read in words here, because there's a lot to parse possibly. Formally, we are asking for any two causal models that is encoding this unobserved nature N1 and nature N2, such that they agree, they have the same causal diagram or selection diagram. In this case, the G of N1 is equal to the G of N2, that is equal to the blue area. And they have the capability of generating the same distribution that is shown in the yellow here. Then they also generate the same answer for the query that you give to the engine, that is the P star of Y given to X. If that's the case, we'll say that something is transportable. That's the idea. That's the meaning, the idea. I mean, this is the semantics of what formally we mean by transportability. Of course, is what I was saying before. We are trying to avoid, given that this is not a possibility, to go over the collection of mechanisms. As I said in the beginning, it's completely hopeless to try to get the mechanism. In my opinion, and all of those cases that I have, I never saw a case that was reasonable to have a mechanism. Then we have this proxy for this collection of mechanisms that is the causal diagram. You have the data that we have, in other words, assumptions in blue plus data in yellow. Is this allowing us to answer the question about the green? Model theory, if you're a mathematician, you understand exactly, I believe, what I mean by model theoretic. Now, we are trying to confront that against the following situation. It's not always true that this will happen. It's important to understand. You say, oh, okay, not always true. Focus on the W here. Assume that someone messed up or forgot to measure, or it was not possible to measure the variable W. Focus on the W. Now, this is the causal diagram or the selection diagram without the W. There's an animation here. The W was here. This was a column in the data set. Someone not measured the W. Now, this is the data that we have. And this is the model compatible with this data collection. Now the question, is it possible to answer the question, Q, P star of Y do X? And the answer is, in this particular case, no. It's not possible, which means that, I'm not fully parsed, but there exist two unobserved natures, N1 and N2, that is shown here, such that they have the same causal diagram or selection diagram, they have the same input distributions, but they generate different experimental distributions. Then, which means that we cannot commit. We cannot say what is the right answer because they are disagreeing about the target of the inference. Then, which in some way could say that our assumptions are too weak at the moment to allow us to avoid to know the causal diagram or the selection diagram in this case. Then just a model theoretical view here, the situation is distinct because in this area that intersects, I just showed two colors here, green and blue, green and red because it's cute, but could be many, could be infinitely many colors, by the way. But there are two parts here of this intersection area that's generating different answers to the P star of Y given to X. Beautiful. This is what we're trying to characterize. So if you are in the case in the left or you are in the case in the right. In other words, trying to avoid this thing about hopefully most scientific findings will not be false. in the future if you are serious about that. And we understand that our assumptions are not enough. This is still symbolic, and it's in terms of understanding is necessary, but usually we don't want to do that by hand. A second type of result that we want, and this is kind of my bias from the computer science department, is like we like an algorithm that will take as input this type of diagram or the selection diagram will return yes or no if the query is transportable or not. If the answer is yes, it will tell us maybe in green is what is in the observation, in the experimental domain, in the source, and in pink it is what is observational that is coming from the target in order to answer the question of the target. And this is just one instance of one possible transportability problem. I'm showing many examples here, I should say, that are baby, that comes 3 variables, 4 variables, some people get uneasy. In reality, I'm just trying to convey the task. Reality is much messier than what we have 3 or 4. Usually this is just one example of some collaboration that you try to get the effect, something related to a lung disease, and there's something about the survival. And this is the kind of setting that we could be interested, or people should be interested. But again, I wouldn't dismiss the baby examples or the toy examples, because I get papers and people don't even have the toy. And when I show the toy, they don't even know how to solve it. And they claim that they can solve with, this is like maybe 50, 100 variables. They claim to solve with 100,000. Not possible. And we like to be systematic and principled in some way. And I think we are going in this direction, which is a plus, or it is a positive. But let's try to understand the examples in a smaller scale first, and then we can kind of scale this up. This is the whole business of computer science and statistics and the data science, is how to scale after we have the principles and the understanding right. I just showed an example that I did by hand. Also, if you're interested, go to the causalfusion.net. This is still in beta. There are a few thousand people now using this tool. That is essentially, you can kind of input. This is just the first diagram that I showed. You see the S node here. This is the triangle, and this is the formula that you get. That there is this averaging by the P star of the age distribution. This is one. This was the second example that we have W. That was the age. Z is the proxy, the language skill, and this is the answer here. You can see the derivation. I think it's a nice one. There's multiple tabs. It's kind of very nice. We're in beta for some time. Hopefully, we'll make it available. It's very good educational tool students are using, and can be for education, can be for profit as well if you want. This is the mediator case. Drop me a line or just go there and enroll. Bias is education academic. Use your university. We are more focused on education at the moment, at least. Now let me go on here. My last observation before I leave to transportability is the following. There is also some belief in the field that, or the discussion, 2 decades old discussion about experimentalists versus the people that is doing the modeling. In other words, it seems that there is some kind of tension. If I can do the experiment, I don't really need to do a causal model. I don't need to engage in this type of exercise. Now, like with what we understand so far, I would like to ask, is the gold standard really golden or really good? And generalizability in clinical trials. Suppose that before what we did, use case here, suppose, very example, suppose that what we did in the, before the randomization, that was the selection diagram of the population. The same triangle here, I just added a new source of exogenous variation, use ZY affecting both Z and Y. Now, whenever we do the randomization, what we get in the trial, in LA, for example, is like we're able to unconfound the relationship between X and Z. That's great. Then for this population, there is no confounding bias in LA. But now what about the generalizability here of this experimental data set when you want to use that in New York, for example, or if you want to use this in the US? Still, it is not there, because this guy here noted that the S, the yellow node, is not disconnected from Y. If you try to average or do this, the first formula that I said, the universal Schrödinger type of equation, this will kind of create a bias here throughout the collider that you are conditioned on Z. If you don't condition on Z, that use the second formula that was like the language skill, we are kind of injecting directly the bias here, bias in S to Z to Y. Then there is no way out here. This is one example about this red and green, that it is not transportable. And still, there's no, is an additive example. The lesson for us is like, even if you have the perfect trial in the population in LA, or for example, one still needs to go to the transportability exercise. You can pretend that we're not doing it, put under the rug, but there's no option in reality. TR theory here is unavoidable. In other words, there is no real dilemma. The experimentalists are getting a piece of the puzzle. But if you have this thing that there's a mismatch in the inferential target, which is almost always the case, we are doing the data in LA, in the UCLA hospital, not just because you care of people that is going to the UCLA hospital. We're trying to make the claim, sometimes about LA, sometimes about the US, and so on. Then it's very common mismatch that we have. Then there is no way of escaping. We just want to be more mature and try to be explicit about the assumptions that we are using, which are available as we discussed. Anyhow, that's my note here, or my final note, at least about transportability. Check the PNAS paper. I think we have examples like that. Now I'd like to take one step back and analyze. I focus on the transportability dimension, where I like to analyze the progress that we made in terms of the capabilities of the inference engine. I just kind of sliced and transportability for some time. But broadly, we're engaged in this exercise of trying to augment the engine. Then as a field report, or as a personal, again, bias, personal field report here, how I see it. Task 0 that I like to call the causal inference from observational studies by Rubin, Robbins, David, and Pearl. That's kind of the triplet. Now I have a crisp understanding about when is a yes or when is a no for this task. And if the yes, there's a few thousand papers written about how to estimate this effect. And it's very nice and robust theory, and still hard to apply in practice, but very nice. Now I'd like to broaden that and talk about causal inference tasks, including what we discuss, or causal inferences. The discussion that we have is about these 3 dimensions that I try to open up that related to the data collection. And what we have: environmental conditions. This is the sampling conditions, and what is experimental conditions, observational, experimental, bonobos or humans, and the type of sampling of the age. This is what we discuss. I focus on the environmental, here the transportability, but the augmentation here, this is just a few references I'll keep usually in the top. We're trying to do causal inference under confounding bias, combined with selection bias, combined with transportability bias. And you can have these different data sets there is this mismatch or this deviation from the ideal protocol relative to this ideal in the sense of this idealized P star of y given to x. Now, many results. This is the focus here about making it more flexible, the data collection. We do have a yes or no answer. Those are a few results. Until very recently, even have results coming out, including from NeurIPS. If you are the machine learning people, this is one of the main ML conferences. Possibly, yeah, check out these papers. I'm happy to discuss. Part of my PhD thesis was about this dimension. Spent a few years on this one. Now I'd like to broaden that. This is what we discussed so far. I put like a little bit ghosty. Now I'd like to open, what about policies? So far we are talking about the doing type of intervention. But this is just one type of, the target query needs to be the do. But do is just one of them. Then maybe you have something that we call the sigma intervention, or soft type of intervention. Again, this is some of the references. Now the engine allows us to give as input this type of query that is about we're just kind of changing the baseline or creating an incentive in the population. I'm not totally want to know what will happen with cancer if I ban smoking. That is like a probability 1, but I would like, if I change the incentives and increase the prices of the cigarettes, how this will affect the propensity of people getting cancer, or the likelihood of people getting cancer. Then now we do have, is a kind of more recent work, but we do have yes or no answer for that. And I'm very proud, and I think I'd like to share that we have something called the sigma calculus, that is a generalization of the do calculus, is the first symbolic calculus for reasoning about soft or policy type of interventions, which turns out to be sound and complete and generalized calculus. Applications here for the ML people, very applied for the data science and the economists and so, any data science serious, but also for the ML folks, this is very related to the applications of policy evaluation. This is just the link to the, I will repeat later, but the link for the CRL, causal reinforcement learning, CRL.causal AI. I have the whole task. This is one of the tasks there that the sigma interventions help. This is one of the tasks that I think people may be interested. Another one that I also like to say is data-driven, and I'll quote here data-driven before someone kill me here in the room. The data-driven in the sense of, this is also references here, check it out, there's a more recent result, there's just one report that I just posted, but I like to focus on this dimension or this input of the engine, that originally you assume that you have this one causal diagram, or you have this, or selection diagram as input. This is not necessarily the case. Sometimes you can use the data and infer something that is called an equivalence class of diagrams. In reality, there are exponentially many, or super exponential. In reality, it's a huge number. We don't do enumeration, but you can take this object as input and put a yes or no answer. This is totally learnable from data. Then this is the first, I would say, the first set of results that we have a causal inference CI pipeline that is entirely data-driven, from assumptions of minimality of the kind like Occam's razor, but we can do something called structural learning from the data, learn the equivalence class, and then we'll have this entire pipeline that is data-driven and complete for non-parametric identification. And I think it's good. Of course, by the way, no free lunch. Whenever we put any equivalence class that is more than one element, that is not a singleton, usually we will get much more no answers than if you pick the correct diagram. There's no magic here. But still, I think it's a good result if you know very little about the system, or if you have some kind of AI system that is interacting in the environment. I think this could be a good initial result. They also hope that this task is interesting, task 5. Task number 6 is related to the estimation. So far, we talk about the decision problem of the engine. But what about if you get a yes answer from the engine? What can we do? In reality, most cases we don't have the P, the probability distribution, but usually we have finite samples from this P. It's here. Now, how can you estimate the effect? Then it turns out that if the answer is yes, now we have recent results and it's still ongoing, and we are learning about that, but how to estimate this effect, the P star of Y given to X from finite samples. Starting from Rubin is one of the reasons that I give credit for him. There are like maybe 20,000 papers or 20,000 citations, 40,000 citations. He has the idea that was ingenious about how we use something with propensity score with a particular set of assumptions or a particular causal diagram that looks like something similar to this one. Now, there was no papers until recently, until 2020, to do, as far as I know, that was doing for any other set of assumptions. It was just about this assumption that is the backdoor assumptions or ignorability. Now we can do estimation for any possible case, including the front door and any other that you have. Again, those are initial results, but I think it's very interesting. Hopefully, can be useful for some. The ongoing, I would say. Now, another type of inference, we are talking about something called layer 2, level 2 of the causal hierarchy or the ladder of causation, that is about the effect of interventions. We're also interested about the effects of counterfactuals, meaning this part of the engine, this type of input here, this is no longer a P of Y given do X, but now we have something that is a real counterfactual, layer 3 or level 3 counterfactual. Suppose that the X prime is the guy, the person took the drug, and Y prime is the person is dead. These happen in the factual world. A valid counterfactual question is, would the guy be alive, that is Y, that is the opposite of Y prime, had he not taken the drug, that is the X, that is the opposite of X prime, that what he did, he ended up doing, or Joe ended up doing. He took the drug and he died. Then it's kind of important hypothetical. Until recently, we couldn't answer general counterfactuals from arbitrary combinations of distributions. Now you can, it's quite recent result, just got last week or 2 weeks ago, one paper accepted as well. Check our CML 2022, starting here. Then you do have this yes or no answer for any type of counterfactual, including nested. I think this is a nice result and very related to policy questions about the effectiveness of the policy. Maybe someone is already trained, and then you can ask, could the person get the job had he not been trained? Is the effect of the treatment or the treatment on the treated? Maybe the guys that are enrolling in the job training program, they are more driven or more effective or more savvy, and they will be getting the job anyways. And Congress may be asking this type of question. without the Y prime here. This is just one example of counterfactual. There are the whole family of counterfactuals that will be here that are allowed by these papers. Now I'm almost done. Something that is very current, like just briefly, I'm almost done, about neural nets, the common question that I get, how is this related? For many years, I was not thinking about that, but we have recent results on that. Now, instead of having the causal inference engine, I call this the neural causal inference engine, that is kind of hybrid between the fully symbolic with the neural type of model. This is a possible neural net that we'll use here. And now from the neural net, you can answer from the set of assumptions that we have in the model, if it's the effect is identifiable or not. I'm very happy, I would say, and sorry for saying like that, but this is the first neural net that I'm aware in the world capable of performing causal reasoning in the way that Pro or me or anyone that is doing causality would say, meaning the neural net will take causal assumptions on this form or similar to these ones, and will be able to decide if the causal question is answerable or inferable or not inferable. So far, there is, by the way, a lot of good papers doing some type of causal inference in the sense of estimation of the backdoor. This is the first time that we have this decision problem that is a canonical problem in causality being answered for the causal net. It's a very recent paper with a collaboration with my students, Kevin and Kaizan and Yoshua Benjo at Canada, in Canada. And I just posted another one doing counterfactual reasoning. There's a new one as well. I just posted it maybe last week in my website. And there's a subtleties why this is much harder, but I will leave it for now, maybe other day, if I'm invited here by Carlos. Otherwise, if he's happy, I'm not sure. My last one, that is also quite recent, that just happened, is about approximations. We are talking about some kind of strict version, or Carlos or Michael, I should say. Michael, I didn't see you. Hi, hope everything's okay. The approximations, we have been talking about some kind of strict type of inference. But the question is like, if you get some references here, including last week's or 2 weeks ago paper that was accepted, what if you get a no answer to the engine? It's very common, by the way. It's because many times the assumptions are not that strong, which doesn't allow in this model theoretic, if you like, to distinguish the models, and then we are kind of stuck. Now here we have the first, in this recent result, we have the first that we can input arbitrary causal model, an arbitrary collection of distribution observation and experimental, and you can get something that's called the bounds. You can approximate the answer. The no answer in reality means that we cannot get a point estimate, but still maybe possible to get, in this case, maybe this is boundable. This is the first general algorithm for bounding when the observable variables are discrete, I should say, when the endogenous variables are discrete. The exogenous can be arbitrary. And because we don't know about them, and I don't want to impose constraints over them. We don't want. But endogenous are discrete, or you can discretize in some way. And this may be very informative. If you're trying to analyze policy, you don't really care about the particular specific value of the effect or even the distribution. You just, many times you just care some kind of null. Is there's a positive, I'm doing here the delta here, y do x1 minus y do x0, the average treatment effect. We just care, is it a zero effect? There's no effect. Is this a negative effect? There is a positive effect of the policy. And depending, we are good with that. Then it's, I think, is a fundamental result here that I think is very nice. The topics not covered, by the way, I'm trying to do the data fusion here. Many topics I couldn't cover today, or there's a typo there, that I couldn't really cover today. One is reinforcement learning, I mentioned, but we didn't cover. Neural nets I think I added the slides. There's a whole discussion about fairness and explainability. Check my website, I'll be happy to get questions, but there is a whole new world here about how to do that through causal lenses. Proxy identification, if you have proxy variables. If you're doing parametric identification and linear in particular, I think we have results that are really compelling, much stronger than IV, and it's kind of amazing. It's still not complete. Still not complete. There is sensitivity analysis that is part of collaboration with Carlos here, and also structural learning. Maybe in the future, just want to give the big picture, and I'm almost done. And I'll start trying to take questions. The first observation that follows from everything is that underlying any system, there is this collection of mechanisms and reality probability distribution over the exogenous as well, the external conditions, called a structural causal model. On purpose, for many years, more than 10 now, I have been telling you that he discovered the structure of the DNA for data analysis and AI. That is exactly the structural causal model. This is underlining there the system that we're trying to do analysis. Now you can kind of slice it in different ways. One way you can try just to explain it. We're just trying to do science, kind of open nature's black box and understand what's happening there in some way. So there is a huge literature in this sense. One is about explaining. We like to do effect identification and decomposition, bias analysis, fairness analysis, robustness and generalizability. I talk a little bit about transportability today. There's a different type of side. This is a different type of side of this coin here about this collection of mechanisms. If you're just trying to understand, it's just a scientist. You can say, Elias, I couldn't care less about science. I'm a pragmatist. I just have my patient here that I want to improve their health, or I have the company that I want to increase the bottom line and have more profits to my shareholders. Then still, the problem that you are subscribed is called decision making, is the other side of the coin about understanding this collection of mechanisms. One name of this type of problem in machine learning is called reinforcement learning. We can run randomized trials. We can think about personalized decision making. And those are two different problems that we have many results. One comment here is about the CRL. Please check. There's almost a 4-hour tutorial about explaining how much progress we could make just by realizing exactly this link here between a structural causal model in the decision making problem when you have the loop, some kind of feedback loop in AI. If you have autonomous car or something that is at the same time you may be doing the intervention and trying to learn or playing a game. Check the crl.causalai.net. But anyhow, those are two kind of sites. Of course, there is some interaction between them. They are studied isolated mostly, but there is some kind of synergy. As much as you understand about the system, you can be more surgical, even if you want to do an intervention. Also, if you understand very little, but you keep doing interventions in the system, you are kind of getting knowledge about this collection of mechanisms. And as part of the line here of CRL is just trying to go in this direction as well. But anyhow, those are kind of, most of the work is divided in this way, the theory, and then you can have applications that is throughout the data sciences and AI and machine learning. I'm very interested in education. Software I just show you that is related to education as well, and can help in practice. Education also, I'm trying to finish a book on the topic and explaining these results for a few years now. In terms of applications, there are two big buckets here of applications that somewhat causality allows us to unify them, but they look very differently. And you need to express some things differently. One is AI and machine learning. The general goal is to have principles and tools for designing robust and adaptable learning system. On the other hand, I emphasize today the data science or the causal data science that we're trying to get a principle or scientific. I put in quote because we like to get the stamp that it is scientific. What this means, or how do you, which kind of legitimacy you have to be able to get this label. But anyhow, the principle and I would like principal inferences from large data collections. That is what we kind of this is what we emphasize today. This is kind of the summary of the work. If someone is interested, we have postdoc positions available in the lab. This slide is usually also for that. Drop me a line. We have a very good team, and we like your help to try to make to fill in the gaps of things that we still don't know. There are so many challenges. But anyhow, my conclusions here, causal data science is a principal framework for combining substantive knowledge about the phenomena under investigation with data to generate causal explanations and more robust and generalizable decision-making. First observation here that kind of triggered the whole discussion, I think so fundamental, not all data is created equal. Most modern data collections are messy and plagued with systematic biases that need to be first understood. It's hopeless if you don't understand. That need to be understood and then be controlled so that causal claims can be made in kind of reliable and robust and reasonable way, I would say. They're robust and generalizable. Not all scientific findings hopefully will not be false. The agenda here that engaging causal data science provides the tools to solve this long-standing problems in the sciences. And I'm talking here about the non-parametric. Parametric is still scarce, and we are working on it, including confounding bias, selection bias, measurement error, generalizability of experimental studies, and more broadly, the data fusion. This is a huge collaboration. It's not only me, of course, there are dozens of people behind that. Thank you, the audience, but also thank you for the Causal AI lab that is in the left side here. I highlight some of the students of the work that I talk here today, and also collaborators from outside the lab that have been helping throughout the years and instrumental. This is just a quote that I will leave here, very related to what I think what we're doing in the moment in history that we're trying to review of this type of thoughts or foundations. But that's it. Happy to take questions, Carlos, or the audience. Thank you very much for the opportunity.
Thank you so much, Elias. That was great. So we do have some questions here on the Q&A that we left until the end because they were more general questions. But before I go to the Q&A questions, I want to open to the panelists if they have any pressing questions they want to make before I read the questions from the audience. And anyone in the panel? Okay, so let's start with a question from the audience. So the first question, so this is a question was a little different from the talk because you didn't go into the ladder of causation, so maybe not everyone will understand this question. But we also have your collaborator Thomas Icard here that can help, I guess. So the question was, where and how do you place past counterfactuals and future counterfactuals in the ladder of causation? Now, future counterfactual for me sounds like an oxymoron, so I don't know exactly how we would frame that question. But I guess the question here is there is some disagreement where to put past and future counterfactuals by some philosophers, and
I can see the question now. Thanks, Carlos. It's the first one, right? And sorry for taking time. I think the person wrote that a while back, maybe 1 hour ago. I don't. If I understand the question, I don't think that we differentiate that. I'm not sure what is future. I'm not sure if one is something that already happened. Like the guy, Joe took the drug. He's dead. Would he be alive? Then this happened. I'm not sure if this is considered the past counterfactual. And the future will be something about what would happen if had we change the inflation rates in some way now, in 1 year from now, what would happen with the, I don't know, job rates and the GDP. Then this is about the future. If that's what you mean by that, I don't think that we differentiate that explicitly. In some way, I think the connection is both of them are hypothetical, or they are about this alternative reality. Then even the past one that supposedly, if my interpretation of past is right, is about something that already happened. The counterfactual world, or the hypothetical, it's not realized. Then in some way that they seem to be of the same nature. But yeah, hope I understood the question and it makes sense. And if there is more nuance, I will be happy to get. I don't know if Thomas is around and want to add something here. Okay.
I can say, I can guess what the question was about, but it might have been about these kinds of cases that some philosophers have discussed, like so-and-so died yesterday, but if they had died tomorrow, then such and such, which are kind of interesting grammatical puzzles, but I don't know how relevant to the subject here.
I see it. Okay, so I understand.
Jeremy, I saw you raise your hand for a while. Do you want to add something?
But if guys feel free, Carlos, if someone wants to interrupt, please interrupt here in the panel. I will hear but anyhow, I hope that this answer is happy to take it offline if there is more subtlety or there's even discussion, I'm not sure if the same kind, but it comes to mind, Newcomb type of paradox or things that have perfect predictors. And so there's nice literature and good discussion there. I would defer in the sense of, I think it's good. I think we are okay with that. I don't see any particular problem. We seem to be compatible. There is no collision at the moment with this type of claim, and there's nice results even trying to reconcile that, at least for Newcomb type of situation. I recommend the paper, the one that comes to mind is the paper with Forney. It's our NeurIPS 2015 paper, Bareinboim, Forney, and Pro, that is about Newcomb-like of problems. But now, moving on here, second question. Is there any way of, or algorithm, do you want to read, Carlos, or to?
Yeah, so is there any way or algorithms to speed up causal inference in order to make causal inference from data stream? Because sometimes we need to make decisions or take decisions, or take actions in real time in some situations such as sensor networks, industrial Internet of Things, and so on. So I guess.
Right. By the way, as I said, there is this whole field in ML that is like about decision making when you have some kind of sequential decision making that is called reinforcement learning, and it's trying to do something like that. And there is the real time and non-real time version of that. And there's a substantive literature, maybe 20 or 30 years at least, of very cool stuff. Mostly oblivious to causal inference in the sense that we are talking. It doesn't do experimentation, and it is causal. It's a common confusion. It is causal or not. There's a lot of drama about, can you put the label causal? Shouldn't we put it? It is totally causal in the sense that it does experiments or interventions in the world. It doesn't use anything that is in terms of these assumptions and understanding of the collection of mechanisms. It has been essentially virtually oblivious. But for the literature that I'm pointing, and there are some papers from my lab and from others, that is this causal reinforcement learning. That's exactly, take a look, Hoan. It's called CRL, CausalRL, crl.causalai.net. That is our attempt to try to marry, we call the marriage between causal inference and reinforcement learning, about how to use these assumptions, how to make it robust, explainable, more generalizable, while we are doing experimentation in real time. Now, and this is still rough meaning, maybe there are dozens of papers, but still it's a kind of baby literature. I'm not sure how, in terms of streaming that you're saying, I don't think there is a literature, I'm not sure if you mean really the literature of streaming, because there is literature of Pietro or people in MIT that's doing streaming. They have like, the stream could be millions of variables and windows moving, and you are trying to cope. I don't think that we have that at the moment at this scale. In causality, streaming in the sense of more probabilistic or other types of reasoning, but it's still streaming. We don't have a causal streaming yet. Maybe, hopefully, maybe you can help us go in this direction. Anyhow, I hope that I answered the question, but Robert wants to say something. Please, Robert.
Yeah, I think my read of the question is, there's a concern for working with a compute intense system like sensor networks or in the Internet of Things that you might have. How can I use these causal models if one time I have to ask a question, I now have to go build a model and train it and then do the inference, but I need to do that. I need the answer right now, and so that's particular user story of I am using this system and it's like I have a causal question, but I don't know what the causal question is until runtime. And I need to make sure that I can answer ad hoc causal questions in real time. It's something that I've been working on at MSR, and I think, as Elias said, that largely the type of logic you need to do the causal reasoning and the logic and the problems that you need to solve to do real time ad hoc query answering is more or less orthogonal, right? And so, say for example, you could implement a causal model as a probabilistic model and then amortize inference prior to for some causal questions that you think you're going to have to answer prior to the real-time scenario that you're going to need to answer them, and then once you've amortized inference during when the problem comes up, that you can answer it quickly. But I think that's kind of where that question was coming from. But I think it's important often to kind of, one of the really interesting things about more broadly about causal inference is that the algorithms that you need to say identify a query and as Elias was talking about with this causal inference engine, much of the time the problems that you need to solve to get it to scale, the problems that you need to solve to reduce variance in the statistical estimation are orthogonal to one another. So you can kind of solve them as separate pieces. Not always. Sometimes you need to kind of think about the interplay between the two, but often you can.
I'll just add thanks, Robert. I wouldn't use the word orthogonal, but can be in some sense. I would just say we need to understand at this level that we're discussing here. Maybe if you want to do in real time, if you don't even know how to do without real time, there is no way of solving it in real time. Then I'm not sure if at some level orthogonal if you have the solution, but if you don't have the solution, it's almost like this is not sufficient. It's necessary but not sufficient, if you want to be more precise in terms of language. But yeah, there are new other set of challenges that will come of how to scale these things up. Really, I think is very interesting. Building on what you are saying, it's not done in some way, of course. And I like, I don't know exactly the particular paper, but the idea of amortizing is very interesting too. I think it's important. But thank you for the question, and thank you, Robert, for the help here. The next.
Yeah. So the next question is from Nicholas. So when sketching a DAG, is the question of whether a variable should or should not be included a trivial matter? Or otherwise, how does one manage dimensionality of inspection?
Yeah, but I should say that nothing that we are talking here, despite of the tone and the style, there's no trivial matter. Everything that we're talking here is non-trivial, at least in my opinion, and examining history and how things happen in practice, and how hard it was to get some of the historical, not only from my reading of history, and it's no trivial. Now, not only that, I would say everything, choosing the variable, not to be included, I would say the hardest two comments or two bullets here. The first one, the hardest thing of everything that we have here is the job of the data scientist. Now put in perspective here, everything that I said, it is trivial. In the sense of, first, we already did it, we meaning as a community, and other, it is kind of very CS or stats-like. The challenge really is about how to have these models. And then everything else should be automated, right? I give you the causalfusion.net. There are other ways of writing that, but whatever, it may take more time or less time, but software and the automation shouldn't be the challenge, because this is done, and this is the job of computer scientists and statisticians and data scientists. Now, the data science in the theoretical. In practice, understanding about the real world and writing down these models and being critical, this is the hard part of the task, because the other doesn't exist. It's more about running stuff. And in particular about the second bullet here about the question, should we include, not include, the heuristic here, this is now no longer algorithm because we are now moving to the terrain of modeling, but the heuristic here is about include as much as you can. Because which means that the model will become more and more detailed. Then if this is needed or not needed later on, even we don't know the downstream task. And Robert's saying, yeah, maybe there are many tasks, but the causal diagram is an oracle for any task that you want. Also, it is already generic. I'm instantiating about you want P of Y given to X, but who knows what, maybe you want the P of Z given to W, or you want the counterfactual, who knows what it is. This is the beauty of the causal diagram. It's an oracle for any possible question, any possible query about this underlying phenomenon. But given that this is the case, the question here is about should we add? Yeah, if it has more detail, depending on the question, maybe this detail that you add in the model, if you know how to add, the algorithm will ignore it. Right? If I add this variable that is very far from where the action is happening and really doesn't matter, the algorithm automatically, sometimes even without we know, will dismiss this part. But now if you move to another part of the model that this is needed, maybe then that's good that we have and you don't get a non-ID or you don't get a loose bound or something like that. Then, but it is not a trivial matter in many, many levels. And modeling is the hardest one. And it's a good question. It's a good question. This is the challenge. I hope that I answered, but moving on here. Thank you for the question, Nicholas.
So the next question is, what do you think we should do about all the existing incorrect studies out there now that we know how to properly measure an effect of interest? When do you think we should hold scientists who make these mistakes in their study design accountable? Okay, so this is a hard question, I guess.
The last part here seems a witch hunt. Yeah, I don't think
this is more. This is...
By the way, obviously, look, one view is like, we should be kind of generous in some way. People are not their fault if they didn't exist and they are not aware of it. Then it is bad, and their job is to get the right inference. But whatever, you live in the real world, and a lot of the best and the brightest and the intentions are very good, then it's okay. Now, if they are aware, then it's another game, right? It's another situation that is like, now you're being negligent, which is not okay. And now that you heard about that, Haya, now it's your job to, I will hold you accountable for not trying to propagate these ideas and help people to get it right. As I mentioned in the previous, this is so hard, but still, it's hard, not hard, it is impossible, in my view, without these tools to get it right. You can do by luck, but this is not the game here, right? You're going to be systematic and get this label science or scientific. Then it is impossible without, unless you get lucky. Then if you want to be systematic, now we have the tools, and you should be pursuing and disseminating and engaging. I'm just one. I'm trying to write my book and give the talk, but I think, and teach my students and engage. But I think we should try to talk more with people and teach them and try to go to the right direction, right? Carlos, I don't know if you have any other idea here, but
and also we need to make this distinction because so the models, so the formal theory allows us to draw correct conclusions given the assumptions, right? So even with the formal theory, we cannot guarantee the conclusions are correct if the input is wrong, right?
But this is a cheap shot, in my opinion. But in your friends, then I can say that. Otherwise, people, this is a cheap shot, right? Obviously, everything in the world is subject to the assumption. When you highlight, yeah, true. Any logic.
Oh, yeah, but what I'm saying, there are two types of mistakes. One mistake is you had the correct assumption, and then you got the wrong conclusion because you had the incorrect method.
But we are not there, right?
Now we can correct.
If you make a mistake because of that, understanding the tools and understanding the models and being honest and getting the wrong, man, this is paradise. Awesome, because then we'll catch the mistake and we refine. Obviously, every scientific discovery is a refinement process to get any real discovery, at least in a serious field, physics. So, man, it takes years, and I'm not being dismissive, but it takes decades sometimes. Then it's a process of refinement and understanding. Then having the right tool to navigate in this way, this is what we want. There is no hope of perfection or doing one-shot learning here for the breakthrough discovery. That's not how it works.
Exactly. So the tools are not allowing us to get the correct answer in the sense of the real world answer, but the correct answer in the way, what is the best answer given the available knowledge, right? Which is
but this is the case for any mathematics. Yes. Mathematics doesn't give any notion in the vacuum. It gives subject to whatever assumptions or axioms you have, of course. But yes, you're right. The only thing that I will add, just to move on here, the time, because of the time, is the nice thing about that in this type of tools and language, we now have a way of scrutinizing the assumptions, because they many times have testable implications in the data. Then if you don't write explicitly, you maybe not even leveraging or trying to, first you maybe, I'm not sure how could you do any inference. But now assuming that you have this written, now is the way that you have the testable implication. Condition independence is one example that was discovered in the 1980s, super powerful and useful, but there are so many other types of constraints that you could kind of try to leverage in order to validate or get any model, any mathematics, just get a little bit more confident about the model. We cannot prove, as we know, that the model is right, but we can try to verify or test the model and start getting more and more confident that this model is at least there is nothing crazy about the model, and it's possibly right in some sense, at least at this level of granularity. Then I think is a very good meaning, promising. But thank you, Carlos, and thank you for the question as well. Next.
So you have an anonymous question here is, I'm new to this space. My background is in robotics. This all seems very interesting conceptually, but the mathematics is a bit overwhelming. could you recommend a few papers or readings as a starting point to get familiar with the foundations?
Yeah, thank you for the question. And robotics is really cool. I hope that I can learn a little bit more. I think it's an awesome field that I'm very ignorant. But I would say the first one that in the very beginning. Oops, 1 second. Where is it? In the very beginning, let me just move here. I give this. I think that. My bias reference here, but I think it's fair given the speaker. I hope they take a look in those are 3 references that I think are nice. One is this causal inference data fusion papers, a survey short one because it's the procedure PNAS. They usually short, but have many pointers to the literature. I'm happy Thomas was here earlier. I'm not sure if he's here, but we wrote this paper. This is iCard. He'll give a talk in the conference. Please don't miss. It's always good. On Pearl's hierarchy and the foundations of causal inference. It's a kind of very didactic, very baby kind of, we're trying to do step by step and explain the best of our abilities at the time, what is causal inference in reality. And I hope it helps. And it was written, by the way, as a companion in my mind, at least, as a companion for the Book of Why. It's very inspirational. You should read it as well. But still, it's kind of more general, explaining what's happening in the area. Here it's kind of more mathematical, a little bit more formal about the language. Then I think those be my initial reference, plus whatever dozens of references that these papers are pointing to. Anyhow, drop me a line if you want more references or if you have problems with some or whatever, if you want to exchange an idea about that. Thank you for the question.
So the other question from Simon is, in the lab versus real world scenario, when is it better to build 2 different DAGs or to add, I guess, the selection nodes directly into the lab DAG?
Right.
In that sense, they are the same task, right?
They are the same in some way. There is some, I'm not sure if they are the same. In some way, there's some subtlety, and I will just talk broadly here. Usually I would say, let's start from the target lab, from the target environment, and then start kind of adding or removing nodes. In other words, it's from the real world to the lab instead of from the lab to the real world. And there are some assumptions about how, fundamentally, there is some assumptions also about what's the relationship between the lab and the real world in a broader sense, because they cannot be completely crazily different. For example, one constraint is about creating the cycles. If you have cycles, even if you cannot unfold the cycles, and then this is not acceptable as a construction, at the moment at least. We just operate in these assumptions that in the models that wouldn't regenerate cycles. Starting from the real world, how to relate to that. This will be the way that the way that I will think about it. It's still open problem. I would say how to learn that from data too. I think it's a good question. But anyhow, that's essentially building 2 DAGs and kind of relating them or checking the invariances of some of the distributions implied by the invariances of the mechanism. There's some also interesting subtlety there, but I don't want to get into it. It's too subtle. Now, maybe in the future if I'm talking just about that. But yeah, anyhow, I hope that I answer. I hope it makes sense. Happy to take it offline if the question remains. Yes, Robert.
Carlos, there was a question from Danielle Ebenhawk under answered that I accidentally dismissed. I just want you to pass it.
So do you want to read the question? I can read the question. So the question is, I work in a field concerned about corner cases. That is, the coincidence of 2 or more variable values have a more significant effect than each variable isolated. We are thinking about probability of necessary and sufficiency to find this coincidence. Do you have, what is your thoughts about the problem statement? So this question is in the answered field.
So sorry, what happened, Carl? Is this answer or not answer?
Yeah, it's in the answered one by accident. So it's
accident. I see.
Second, yeah.
The Carlos doesn't like you. Then it's
No, it was Robert. Robert answered it.
Oh, my fault. I was.
I didn't see. Okay, this is Robert and Robert. No, I will need to look. I would say that I will need to look in the problem more specifically. Because a lot of the inference that we are doing, the graph in some ways is kind of general. I say non-parametric and parsimonies and so on, but it's very non-committal in the beginning to the particular form of the functions. In other words, it doesn't commit to the specific values of the effect. It could go, it may be that you do and there is a huge effect, it may be there is a small effect, and it kind of does, this is the part that is quantitative, this is qualitative. The quantitative part comes from the data. And depending on the particular data set that you draw, this is happening. Now your problem seems to be about some, if I understood, because I didn't read the question, but seems to be something related to the magnitude of these things. Then I'm not sure if there is something else. What could be said in addition? And if you want, by the way, if the person is still here and wants to speak up, please, we'll be happy to hear from you. And I don't know if Thomas wants to say something.
I actually just had a question about something that I didn't quite understand. And one of the points that you made, there was a slide about the sort of purely data-driven kind of approach that you could do. And when you said something about like inferring an equivalence class of graphs and then using that, and I just didn't understand what was going on there, because I would have thought that the equivalence class is basically just implied by the distribution, by the observational distribution, and then you don't really get anything above and beyond the observational distribution. So what are you actually doing there? If you could just say a little bit more about.
There are some hidden assumptions, right, Elias?
Yeah, it's me.
I don't see this.
No accidental cancellations.
This kind of thing. Okay.
I wouldn't say it's. I didn't see that it's hidden, but anyhow.
But it's like the usual faithfulness, whatever.
Faithfulness. I don't think that Carlos. I don't think that Thomas is in this sneaky move here. He's just genuine question.
I just don't know what you were doing.
Yeah, I know. The Carlos is already. We know that. Faithfulness. But I think even under faithfulness could be surprising. I think this is the point. And the point is like when you are able to reconstruct. And I don't need to. Anyhow, I can share examples. But when you are able to reconstruct the equivalence class, for example, a tag, a partial ancestral graph. Then you get some orientations, and you get even some parts of the graph that there is this V node, that is the visibility, that there is no inducing path or between two nodes, for example. Then from this kind of fragments, it is possible to get some causal effects that is not explicitly in the observational data.
So I see. So is a way of putting the point that if you tried to do it sort of purely in the calculus, in the sort of symbolic calculus, then there would be no natural way to kind of encode the assumptions that allow you to generate the further estimations of causal effects. It's a way of basically saying, if I assume faithfulness or whatever you need to assume on the graphical side, then you sort of get more out than you would have been able to easily encode in a way that you could understand just in purely symbolic terms.
No, not exactly. In the sense of again, and I was not so sneaky, I think, or I try not to be callous, because I did mention that we have some kind of.
No, you weren't. I was just.
No, it's not detail, by the way. It's guessing that we mentioned Occam's razor. There is some kind of minimality or something like faithfulness, like something. It is very strong, I should say, but let's put this aside. Even if that's true, I think this is the discussion with Thomas. How is this possible? What is the real statement here? The symbolic, this is the thing, all the machinery that we have for symbolic, like do calculus or something, or sigma calculus now, or this is the only input that they take is exactly one diagram. Now, what we're doing here is like assume that we run these algorithms under whatever assumptions we have that we already discussed, and then we got the equivalence class. In reality, the equivalence class is exponential, usually a super exponential number of diagrams. An alternative, what we could do is the following. You can go over each diagram, each member of the equivalence class, run the calculus, and get an answer. If they are all 1 billion, 1 billion is not hard, by the way. You can usually have this in algorithms class, things blow up very. If you get this 1 billion effects and they are matching, then you will say that they are identifiable here. Now, the whole drama or the whole challenge here is like, obviously, we don't even know how to enumerate this 1 billion because the object is the PAG is a complicated one. There's no algorithm of enumerating all the elements of the thing. And also, even if there was, it's totally impractical to do. There's no way of really running this computation. Now, the whole agenda here, the whole challenge here is about can you operate? It's almost like having a calculus. This is a result that came last week or 2 weeks ago. Do you have a calculus that you can operate similar to the do calculus, but on top of this object that is encoding these 1 million graphs? Then that's the kind of result. Until this paper, by the way, 2019, we didn't have a calculus. We didn't have an algorithm. In other words, we have I think Clever. This is work with my PhD student, but Amin Jaber, soon in the job market. Given the challenge there, because when you have the DAG or something like that, or DAG with latents or IDMG, there is a very crisp factorization, and there is a connection between how to run the algorithm and how to massage the factorization. When you're operating on these equivalence classes, there is no such a factorization. It's the whole mass, because you don't have the orientation of the arrows and you don't have the bidirected arrows. Now, the work with Amin is about, can you have, mostly you heavy lifting from him, I should say, but how can you kind of have this flexible factorization that allows for the structure uncertainty that are inherent or is the signature of the PAGs or the any equivalence class. Then we have that, and then we have the algorithm and the factorization playing together. More recently, maybe 2 weeks ago, and it took maybe a few years, now we have also a calculus that I know that you like and I like it too, but now we have also a calculus that you can operate there, then you can do by hand and understand. But still, I think the algorithm, for most people, they want the algorithm, right? They just want to input and in some kind of effectively in polynomial time getting a formula, a yes or no or a formula. But we do have an algorithm, a calculus now as well. But you understand the complexity, you understand the challenge or the complexity, right, Thomas? Makes sense what I'm saying?
Yeah, that makes a lot of sense. So the way that this is possible at all, or the only case in which it's interesting, is in the cases where some assumptions allow you to at least reduce the space of possible graphs by some assumption, such that then it's an interesting question how this sort of abstract characterization of the entire equivalence class can get put together with your observational data, say, to generate your conclusion.
Right.
Like if the whole thing is not interesting, but if it's smaller, then it's interesting.
No, but if it's huge, it's interesting too. The question is like, if you don't, I would say we don't control the size of the equivalence class directly. In other words, it could be, and I think it's very interesting if you have 1 million nodes, 1 million graphs, diagrams in the equivalence class. That's the interesting because it's more useful. If I have 10, I can run by hand. But but it's 1 million. But the faithfulness of this kind of assumption comes from the fact that if you don't have it, any possible structure in the world is almost like there is the God pulling the strings there. It's like a puppet, what's going on with the observable, which may be true, but the theory will say that you cannot do any inference. Then I'm not overly, I understand, and by the way, I don't want to be dismissive about people against Occam's razor or simplicity type of assumption. There's good discussion there, there's workshops, and I'll be happy to discuss, but still, I'm okay with that, because otherwise we cannot move. We're in this theory of the puppet, kind of everything in the observable is being pulled from outside, which the theory, rightly so, is not even more computational challenging. Computational is very easy, because then nothing can be answered. We don't need to spend any time. It's not about the size, it's just about anyhow, if there is this super latent variable that is affecting everyone, then it makes sense, Thomas. Okay. Cool.
All right. So, we have one, I guess. So this would be the last question. So, Marco, because you're already running out of time.
Sorry. Thank you. I'll try to keep it short. I'm very much on my depth, so please let me know if this makes sense. So in the beginning, I got the feeling that you said you're in this discipline, you're mostly agnostic about mechanisms, right? You just work with graphical models and distributions. But at the same time, and I think the point about amortized inference might be relevant here, at the same time, it's useful to have a implicit understanding of mechanisms. So for example, if you have a graphical model, some quantities or constructs are actually composite. So there's underlying causal factors or quantities that are driving these relations. So if you would have a very complex model, you would, I assume, benefit from having mechanistic understanding. And then the kind of second question related to that is basically, is this discipline, this causal inference stuff, able to basically provide any leads on what extra data you should be looking for? So for example, what extra sampling, what extra question answered would lead to the causal inference problem being resolvable when it was first unresolvable? Does that make sense?
Yes. Thank you for the question, Marco. The first one about mechanism, I don't know if it came across to both. This is my perfect. We are totally compatible with the. But let me put it me. I totally believe in the mechanism. I think this is the starting point of everything that we're doing here. Is the acknowledgement. Let me find it. Is the acknowledgement that the mechanisms are there. Yes. Then, in other words, I'm a mechanist by heart, and I have challenges with non-mechanistic type of understanding or non-local type of stuff, and I will maybe in the future we can have another talk about quantum stuff. But the point is, like, personally, I believe in the mechanisms and I believe in the mechanisms. I think it's all the state. Mechanisms are there. This is the starting point of the analysis, and this guy here, this object that we're showing, is just a surrogate for this collection of mechanisms.
Exactly.
And this is one of the differential. There are people that may not even believe mechanism. I will not start doing the literature review here, but there is discussions that is going on from decades about people that is not mechanistic or doesn't believe in this collection of mechanisms. I'm not one of them. I'm in the camp of the mechanism. Now the mechanism side. Now but your question is non-para, and then my statement in the discussion here is about the non-parametric type of mechanism or analysis, meaning I don't want to impose, or we don't want to impose constraints about the form or shape of this mechanism. Is this possible? How it goes? Because it's the least committal of all kinds of analysis. That's the discussion. Now, many times we'll get as we discussed, we get a negative answer, meaning we get a no answer. Then there are different ways that you can escape or can kind of move around the no answer. One of them is we alluded to, in some way, you're alluding to both. One of them is just to assume something about the mechanism. We have also papers on that. That is like, if you assume that this guy is not linear regression, but this guy is from some linear class, not linear regression, I will not get into the discussion what this means, but this is linear. Then there are so many results that you can get that you can flip a no answer to a yes answer. It's very beautiful, totally compatible, could be graphical models, or you assume that we spend maybe more now a good amount of time, maybe 3 or 6 months, 3 months, or monotonic. How can you add monotonicity here and maybe you get more results? There's no non-published. Then, in other words, this is essentially a constraint over the space of the mechanism. Then this is totally fine. My my discussion here or the approach here is just let's start from the least committal and try to see how far can you push, because exactly we're trying to avoid what Carlos was alluding to. We don't want to introduce our modeling mistakes or errors because the analysis is totally contingent on these assumptions. Then that's the goal of being least committal. But still, if you get a no answer, one escape is what else can you assume in order maybe that is reasonable and plausible and defensible such that you can get a yes answer. This is one line. Then not against the mechanism. The second one, I don't want just to start, I don't want to start from fully claiming that we know the mechanism because it's totally nuts, because it's so hard. If you say that it's hard to get the graph, as people say, the mechanism is orders of magnitude harder because the graph is just encoding the scope of the mechanism. Now, this is one line, but anyhow, finishing my bullet one. Bullet two is what you refer to, that is which kind of data, additional data, maybe, in other words, the answer that we get for this question, about a yes or no, is contingent as well as the particular instantiation of the data that we got. If this is the particular combination of data sets, I have a do Z and a do W, and I want to do a do X, from this set of assumptions, maybe non-parametric, I can get a no, I ended up getting a no answer. Maybe you cry, you get some drinks, the next day when you come back, you say, well, whatever, maybe you can measure another set. Maybe I can have a do, I don't know, the do Z now that I didn't have before, or the do, some other name, do A. Then maybe the do A will allow you, in other words, you can even hypothesize. You can say, what about if I have another data set do A? Running the engine say, okay, now this is okay. With this set of assumptions, maybe you are able to get the answer. In other words, there is these two different ways, these two different routes. There are others, by the way, but there are two big routes of ways. One is like, can you make stronger assumptions than being fully non-parametric that comes from this side? Alternatively, can you enlarge the data collection in a way that maybe these assumptions will be okay? Then it's totally fine. I wouldn't say that we have this everything closed in the loop, that everything is working beautifully, but it's totally possible even to play it this way. We still don't have the automated science, the fully version of that, hopefully, but still, I think all the ingredients are here, and you can play everything that I said here. You can do in the way that I'm saying. I hope it makes sense.
Yeah, because very briefly, basically what I'm getting at is you have the tools to also build in a curiosity in the causal inference engine. Is that correct?
Yeah. This is a fancy name that is coming up now recently. Yeah, beautiful. Yeah, I think so. If you want to sound fancy, no, I like it a lot, Marco. I appreciate it. If you want to say that the agent is in this side and is thinking, and say the agent is wondering, should I do the intervention on the do Z now, and I didn't have, what would have happened? Would I be able to? And then, that's beautiful. That's beautiful. I really like it.
Well, thank you, first of all. Thank you very much. That was great.
Yeah, I appreciate it. Yeah.
So I think we need to wrap up because we're already half an hour over time. Well, thank you for hanging around, Elias, and being generous, answering all the questions.